Hello everyone. Today we're going to start section 15.4, application of a double integral. We're going to talk about several applications. Okay. This section we're going to spend 2 days, and then today we're going to talk about the first part. And if you look at our schedule, tomorrow is the review, and the next Monday we're going to talk about the second part. Okay, let's get it started. Okay, so this is a lecture 17. Okay, section 15.4. Applications of double integral. Okay. Well, the first one, we look at the density and the mass. Okay. Now, if we review, we say z equal to fxy. We said this is a surface in space. Okay, and then we say, well, the double integral. We said the double integral of this function on plane region D. So this is fxy. Okay, and then here we say dA. Now, from the derivation, we know, well, if this is the height, the z value at the given point, and then this one is a small area. Okay, the area times height, this give you volume. Okay, this give you volume, and then we say, well, this V, that's the total volume. We say this is the total volume. Okay, total volume, we say that's the volume of the solid below surface, below the surface z equal to fxy, above the plane region D. Okay, now here we say if the integrand replaced by rho xy. Okay, if this one represents the density. Okay, the density, well, of course we say, suppose we have a piece of material. Okay, we think about it, the material made by something, and then we say, well, at a different point you have a different density. Okay, density is, say, here's the mass or units of the mass per unit area. Unit area. Okay, we say at point x, y. At point x, y. Then we have this. Then we say, well, if you consider the double integral, so this is a d, and this is rho x, y, and then here again, dA. Now this time, we say this is a density. Well, that's mass per unit area, and then times area. Then this give you, well, the area can, here is a mass per unit area times area. So this is the mass. Okay, that's the mass. And then we use this notation m. So we say this is the total mass. Okay. The total mass. Okay. Well, you think about the piece of nominal, and then if it's not uniform, so they use different material, and then some part has a higher density than the others. Okay. Well, of course, we say we have a function to describe that. So that's give you that. Now, another case is, say, here we say if the integrand uses sigma xy represents the charge density. Okay, electricity charge. Okay, so we say this is a charge per unit area. Okay. Then, well, of course, at a point, then we say this double integral on D. So we say this is sigma xy, and then the dA. Now this one we say this is a charge. Okay, and this is the area, or we say charge density. That's charge per unit area, and then charge per unit area times unit times area, and then so we say this is the charge. Okay, this is a charge, and then we use notation, say Q, we say this is the total charge. Okay, so you see, well, depends on the integrand. That's the function in the integration, the meaning of integrand. Then we have a different application. Okay, so the derivation of the definite integral is the same. Okay, so here we don't need to repeat that. Okay, now let's look at one example. Okay, example 1, we say electric charge is distributed over disk. Over disk, say here's the x squared plus y squared less than equal to 1. So that the charge density the charge density at xy is giving, say, sigma xy equal to square root of x squared plus y squared. Okay, well, this is C per square meters. Well, that's the unit of the charge density. Okay, and then we say find the total charge on the disk. Okay, so this is the example. Now here we just directly use the integration we just talked about it. So we say, well, Q is equal to this double integral over D sigma xy dA. Okay, where we say D is equal to, now notice this, if the disk, and notice the density function is square root of x squared plus y squared, so we probably should use the polar coordinate. Okay, use the polar coordinate, and we have a very simple description of the region. So R is between 0 and 1, and the theta is between 0 and 2 pi. Okay, of course, sigma, if you change to r theta, so that put r theta, so that's what equal to what? Equal to, you say, square root of r cosine theta squared plus r sine theta squared. Okay, so this is equal to r squared. R is positive, that's equal to r. So that means this integral become 0 to 1, and then 0 to 2 pi. And then we say this is r. Remember, dA is equal to r dr d theta, equal to that. Okay, so this is equal to, okay, so here we have 0 to 1, and then with respect to r, let me see. I think I think I put it the order wrong, right? I think I should put it d theta dr. Yeah, d theta dr. We should put it like that. Okay, so you see, with respect to theta, r is like a constant, so r squared will move out, and then the integral is 1. The antiderivative is theta, so plug in 2 pi, 0, then dr. Okay, so this is equal to 2 pi, and then 1/3 r to the third, plug in 1, 0. So that's equal to 2 pi over 3. So that's the total charge. Okay. Now, second application, we talk about moment and center of mass. Okay. Now here we say moment. Okay, let's look at the definition of a moment. We said the moment of a particle about an axis. Okay. Is defined to be the product of its mass and its directed distance from the axis. Well, this is a definition from physics. Now, here, well, let's see. Let's draw a graph on the side. Say here, if we have a planar region, okay, say this is a, suppose this is a D in the XY plane, okay. If we want to study the moment, what we do is we do partitions, okay. Okay, we do partition, okay, on the y variable and also on the x variable. Okay, we break it into small pieces, and then we consider one piece. Okay, if we consider one piece, and then let's put it this let's draw it separately. Okay. So if the piece is small enough, we can assume the mass is concentrated at the center. So here we say, well, suppose this is the small piece rectangle. So this is Rij, and the center. Okay. So here we say, well, this is center. We say is. Put it here. Okay, so we said this is Xij star, Yij star. So that's a point. Okay, and then this distance. Okay, so this distance, we call it Yij star. Okay, now let's see. If we say the moment of Rij about the x-axis, okay, is approximately, I put it this, well, let's look at it. First of all, we calculate density at this point, okay, so we use the density at the center of the rectangle Yij to approximate it. Well, we assume if Rij is small enough, we have a uniform density. Okay, so we use this one. Then times the area, Now, you see, this is the density. Well, the given density is not uniform. But since the Rij is small enough, so we assume is a uniform density. And then this is the area. Well, density is mass per unit area. So this is the mass, okay? Mass. And then here is a Yij star. So this is the directed distance to the x-axis. Distance. Okay. Now you see the product of mass and the directed distance. So this is moment. That's the moment. Okay. Then we say the total moment. The total moment of D about the x-axis. Okay, become this. So we say mx is equal to, well, we put it, you see, we do partition, approximation, summation. Okay, because we have two variables, so the summation is I from 1 to m, j from 1 to n. And then, okay, we move this yij star in front, and the row xij star, and then yij star, and then delta a. Now we take a limit as m, n both goes to infinity. Both go to infinity. Now this limit, we say this limit, if it exists, that's just a double integral. Okay, now this time the integrand is y times the rho xy dA. So that's the moment. That's a total moment about the x-axis. Okay, then similarly we say the total moment total moment of D about the y-axis. Okay, so this time, well, we say we use m sub y, so that's we're equal to this double integral. Here's x times the rho xy. Well, you imagine. So imagine, well, this density area, that's equal to mass times the distance directed to, well, at a point xy, the distance to the y-axis is x. Okay, is x. So we have this. Now, so this talk about moment. We have the two formulas, and then we say the center of the mass. Okay, center of mass. So it's defined to be x bar, y bar, and x bar is equal to the moment about x-axis, m sub y, over the mass, and the coordinate of y is the moment about y-axis over mass. Okay, mass was earlier in part 1 we derived the formula. Okay, so now this part, I don't need to talk about too much, and then if you want to review in chapter 8, we talk about moment and the center of mass. Okay, that's there we talk about single integral, and then here is a double integral. So how about let's just look at one example. Example 2. We say find the center of mass of a lamina in the shape of an isosceles right isosceles right triangle with equal sides of length A if the density at any point is proportional to the square distance, square of the distance from the vertex offset to hypotenuse. Okay, so it's like this. Now here we just give a shape of the lamina, which is a isosceles right triangle. So that means one angle is a 90-degree right triangle, and the isosceles, so you have two sides equal to each other, okay, and the sides is the length is given, and then we say the density is at any point is proportional to the square of the distance from the vertex opposite the hypotenuse. Okay, now this type of problem, if you set up because we can set up the coordinate system the way we want. Okay, because there's one angle is a 90-degree. It's natural to think about you put the two sides on the x and y axis. Well, theoretically, you can put it any way you want. You put it differently, your answer should be different. Okay, so here, how about we just put it like this? Okay, so this is a x, this is a y. And then this is a D. Now this side is a A, this side is a A, right? Then the origin is the vertex. This is the hypotenuse. Hypotenuse, we have an equation x plus y equal to A. Okay, you can write y in terms of x or x in terms of y. Okay, and then we say, well, because I choose the vertex to be the origin, therefore, we say sigma. Okay, we just say choose the coordinate system as this one. Therefore, we say the density, because it's proportional to the square of the distance. So that's x squared plus y squared. Okay, that's equal to this. Now, when you look at this, we say by symmetry, So by symmetry, we should know this. We should know the center of a mass. The x-coordinate and y-coordinate should equal to each other. Okay, because the geometric shape of the triangle, well, you see it's a symmetry about y equal to x. If you draw a line y equal to x, it's a symmetric. And the density function is, in terms of x, y, we say is a symmetric. Okay, so you switch x and y, it doesn't change the density. So that means the x bar, y bar should equal to each other, which means we only need to calculate one of them. Okay, so here first of all we describe a d. Okay, so this is the x, y, and then, well, we can describe a x first between 0 and a, and a y between 0 and a minus x. Okay, so this is a y equal to a minus x. That's this line. Okay, and then now first of all we find the mass. So the mass is say from 0 to a minus x. Okay, rho is k, x squared plus y squared, and then we say dy dx. Okay, so we have this. Here, let's see, if we try to evaluate k move out, you first of all with respect to y, so 0, a. So you're going to have x squared y plus 1/3 y to the third, right? Plug in y equal to a minus x, a equal to 0, dx. Okay, so when you plug it in 0 to a, you're going to have x squared times a minus x plus 1/3 a minus x to the third dx. Okay, now of course you multiply out as a polynomial and then you can integrate. In fact, the last term you don't need to multiply. You do substitution that u equal to a minus x. Okay, I'm gonna let you verify that. Okay, just a couple more steps, and then we say this is equal to 1/6 k a to the fourth. Okay, so it's equal to this, and then well, let's calculate this moment about the x-axis. So this is a, let me see, we talk about moment about the x-axis is a m sub x. So this is equal to, we say 0 to a minus x. Then we say, well, k x squared plus y squared times y. Okay, times y, and then dy dx. Okay, and then this one, you do the same, 0 to a, you multiply out. So here you have a k. So for example, you have here is x squared times y, the antiderivative is half y squared, and then plus 1/3, the y to the third is 1/4 y to the fourth, and plug in y equal to a minus x, y equal to 0 dx. Okay, again when you plug it in, and then you're going to see here 0 to a, and let's just write one more step, k, and then we have x squared, well 1/2, and then a minus x parenthesis squared. Okay, and then this one is 1/4 a minus x parenthesis to the fourth dx. Okay, you just integrate term by term, and then the first term probably multiply out, and the second term do a substitution. So I'll let you verify that, and then this will equal to 1 over 15, and then k a to the fifth. Okay, therefore we say this implies we say y bar, which is equal to m sub x over m. So that's equal to, if you plug in 1 over 15 k a to the fifth, 1 over 6 k a to the fourth. After do the cancellation, so you're going to 2a over 5. Okay, now if you have a y bar, you can have x bar, we say. Therefore, we say the center is x bar y bar is equal to 2a over 5, well, which is the center of a mass, 2a over 5. We say if use the above coordinate system. Okay, well, we have to say this last sentence because if I choose the coordinate system differently, so for example, if I the triangle, if I don't put it this way, put it in a different position, of course the center of mass will be different. And I think this probably is the easiest one. And if you put in other position, maybe the calculation is much harder. Okay. Well, today I'll just talk about 2 applications, and then on Monday I'll talk about another couple of application. Okay. So here this is. Okay, so this is a section 15.4. Okay, 15.4, and this application of a double integral. Since we haven't finished this section, okay, we're gonna finish on Monday. So this section will not be on the midterm on Friday. Okay. But I think say here this is tomorrow's lecture, so Thursday I'll give you a brief review. Okay, just outline the midterm. Okay, so please check out, watch the video. Okay, please review the midterm. Will cover the lecture up to yesterday's. Okay, so that means up to Tuesdays. Well, today is Tuesday, and this is the one I just recorded is for Wednesday. Okay, so I'll talk to you next time. Okay, bye bye.